Hello, everyone. I'm Professor Tina Burns, and welcome to Lecture 7A for the Computer Architecture class for Rutgers University for the summer of 2025. And this is the first lecture in week 7 of our class. We're actually coming to the end of the class, and all that we have remaining next week. So we have a few slides to cover this week, and then next week, of course, is the final exam and the project. So let's get into what we're going to talk about for this lecture. So we're going to go over some of the basic computer architecture concepts. We're going to talk about pipelining. We're going to look at instruction flow with and without pipelining. And then we're also going to look at pipelining data hazards. And finally, we'll end with discussing some parallel processing techniques and architectures, including the SMID and the MIMD. So before we talked about, anytime you want to teach something or you really want to understand it, you want to have a good idea of how you want to represent it. So we've developed this we call a computer architecture modeling system that we use to represent data flow for memory, for instructions, and it just helps us to get a better understanding of how we are processing information in general for a computer. And we talked about all during the class, kind of this von Neumann concept, right? And a few things that are very important about this is it's going to model how computer architecture works for data flow. It has one memory space, right? So that's one memory bus. And also, the programs and the instructions are stored in the same memory. Now, if you remember from our last conversation, the von Neumann model is going to have your input and your output. It's going to have a central processing unit, an arithmetic logic unit, and then some sort of memory bus, right? So those are going to be your common concepts or your common parts of this architecture. Now, that's going to be relevant today because we'll see how that impacts the speed and operation of your computer. And we'll also talk about a different model that can be used to avoid some of the hazards and different things you would come across with the von Neumann model. We also talked about when you have a computer or in computer, there's really three important groups of factors that you want to consider. And that's going to be power, processing, and memory. Power is how long can your program run and how much does it require? We didn't spend too much time on that. Now we talked about processing and Amdahl's law, and how we could make things run a little bit faster. And we spent the last couple weeks talking about memory and how we could improve that through things like hashing and different elements there in order to enhance the memory process and give us the ability to access. I'm going to change this a little bit. Give us the ability to access and handle those memory process a little bit more rapidly. Now we're also going to talk about today, we're really going to focus on how to speed up processing. Now, processing involves how we handle our data. How do we make it so that we can get and retrieve data a lot more quickly so that we can handle instruction operations a little bit more quickly? Well, one way you can do that to make your program and your computer a little bit faster is by a technique called pipelining. So, pipelining, uh, it's something that's used in computer architecture to help improve your instruction throughput. So when we think about instruction, right, we spent several weeks on assembly code and learning how those instructions work, right? You have to load memory, you have to put that in a specific register, you perform an operation, and then after you perform the operation, what you do is you go ahead and then write that to a memory address so that it can be accessed later, right? And depending on how that moves, your throughput can be slow or it can be quick, especially depending on how you set up your cache and whether you have a level one, level two cache, and how quickly you can get and attain those the information from memory. Um, but it's not just about memory, but it's also about how you process the instructions as well. So what we're going to talk today about is how to improve that. And that can be done through pipelining. Now, when you have pipelining, we have up until this port. point, considered doing these instructions in a single flow. That means we're looking at one instruction, we complete that instruction, then we move on to the next instruction, then we move on to the next instruction. Pipelining is a process that allows us to do multiple and handle multiple instructions simultaneously. All right, so I really don't like the way this is looking. Now, it does this by dividing your instructions into a few different parts, um, so that you can take each part. And by the way, we're talking about instruction pipelining. So you can take each part and then break them up into stages, and you can handle those stages independently in parallel to the other processes that are running. So as I said, it breaks it up into several parts, which means you can handle several things at the same time. So let's look at our standard flow. We have an instruction fetch. That means I need to get the instruction. That can be a add A and B, right? That's your typical instruction. You need to decode it, meaning what does this mean to the compiler? How am I going to go ahead and process that? Once you then process it, you're going to access memory and your registers in order to be able to um, determine where you're going to put this data and where I can access it from. Then you're going to write to the block and you're going to go ahead and execute the command. So these are kind of these five areas of interest when we look at a standard flow. And we look at this standard flow, you can kind of see how it looks, right? If we use these letters just to substitute for it, right? Typically, when we look at these a lot of times, you might not see all of them. I have five stages. Let me go ahead and get this annotation out here. I have five stages, but a lot of times people will just use the fetch. Actually, let me not do that one. They'll concentrate on fetch, decode, and execute. So these will be the common three that you'll see. I have five listed for a reason because I wanted to really think about how the accessing the memory impacts the flow and the pipeline of the system overall. So I have five, but typically sometimes you'll see it just with these three: fetch, the instruction decode, and the instruction execute. Let me go ahead and make this consistent in terms of uh, I want to be consistent in all that I do. So if I'm going to do this, let me make these all capital here. Okay. So again, then let's go ahead and do that. We have uh, these operations here. So if you see this throughout the presentation, this is kind of what I'm associating them with. Getting the instruction from your instruction or program register. You need to decode it. That means what is it telling me to do? I need to access memory. So what register or memory block am I writing this to? Then I need to write that instruction somewhere. And then I have to actually execute that instruction, meaning if it's telling me to add something, then I need to perform that addition and make sure that I store that somewhere. All right. So those are those five steps. And if we were looking at this as a standard flow, that means there's no pipelining. Let's say that each of these sections of the each of these instructions take one clock cycle. Let's just say that they take one clock cycle. They may not actually take one clock cycle, but we're going to use that for example. That means that in a standard configuration, I need to finish all of these. It's going to take me 5 clock cycles. Once that's done, then I would fetch the second command. In order for me to do the second command, that's going to take another 5 clock cycles. Then I would fetch this third command, and that will take me another 5 clock cycles. So what happens with that is that now I am taking 15 clock cycles in order to perform this specific task. Now, that also means that while I'm doing this, if this is just accessing one part of memory or one part of the processor, um, or one part of my computer architecture, everything else is kind of it's standing idle. So it's just not a efficient way to use our resources here, right? So how can we enhance that? How do we change that? Right? If I know only part of the processor or part of the computer is being used at a time, what I can do instead is pipeline it. So now notice how I changed it from here to this next section. Here, everything is this is waiting until this is done. Here, what I'm doing is I'm changing it so that as soon as I fetch the first instruction, while I'm decoding the first instruction, I'm going to fetch the second instruction. While I'm decoding the second instruction, I'm going to fetch the third instruction, and these are all happening in successive clock cycles. So now something that previously took me 15 clock cycles is going to take me 7, assuming that there are no conflicts or hazards, right? So now I have cut down my time tremendously because I'm able to kind of perform these back to back to back to back without the other areas of that computer system being dormant. Now, if I do it this way, this is called pipelining, right? Just instruction pipelining, by the way. If I'm doing this instruction pipelining, then what happens here is I am now doing several of these instructions simultaneously. I'm saving time and I'm using more of my space. So since we talked about space, let's go ahead and look at this practically, right? Now, we're used to seeing these. We spent a fair amount of time looking at assembly language and all of those things and all of those kind of instructions, right? So this is a like a pseudocode. This is not exactly what we're looking at, but we're just going to consider this as pseudocode for our assembly language. And this structure, this diagram is all based on a von Neumann model design. All right, I have my CPU. I have my memory addresses. I have my arithmetic lot. I have my control unit and the arithmetic logic unit. And then I have whatever's going on with my input and output. And I have one memory bus. It says memory address, but this is really our memory bus. Um, I'm gonna go ahead and change. I don't know. I'm gonna change that here. Really, this is our memory bus, and that's what we're using this for this entire thing here, right? This is our memory bus, which means that for these, I only have one. I have one memory bus for the entire thing, as opposed to having multiple. Now you'll see how that impacts us as we go on in this in these examples. All right, so I have this memory bus. I have everything going through this memory bus, both my instructions as well as the data that's kind of going back and forth, just this one bus. So there can be kind of some conflict sometimes. But let's look at the flow overall. So first thing I'm going to do is I'm going to, from the CPU, I need to fetch the instruction. That means I need to get this instruction and determine what the memory is. So there's just going to be this one area, this one thing doing it right now, and I'm only dealing with the control unit. After that happens, what I need to do is update my program counter to say, hey, I have an instruction that I want to handle. Let me go ahead and do this. In addition to that, let me see if I can decode what this instruction is. Once I get this information, for this one, we're going to assume that we have these other ones I'm updating my instruction counter. And then I'm performing this operation here. I'm performing some sort of operation here, right? That's going to be the last thing I do. And then after I do that, after I perform this, then I can kind of go on to this next step. But the issue with this is that I cannot move on to, so right now I can move on to this one. I can do this load command here, but I can't move on to this next command until all of this is done. And notice how I'm only using a portion, excuse me, I'm only using a portion of this, of these elements here. I'm not even using the rest of this. I'm only using this function of it. I'm not doing anything with the program counter. I'm not doing anything with any of the other elements here. I'm just waiting for this particular item to complete. That is not a very efficient use of our time here, right? If we look back at kind of where these things were flowing, I go from just fetching the memory to updating my program counter to getting the instruction to a point where I'm able to take this and do this load command, right? And get the information for the load, but now all this other stuff is sitting empty. Now let's look at that again. So that means I'm not doing anything with the arithmetic logic unit. Right now, I'm not doing anything with program counter. I'm not fetching another component. I'm not fetching the next address from memory. All I'm doing is just this one command. So everything else is sitting idle. That's not efficient. That's not an efficient use of our resources because 90% of the other items or maybe 70% of it are not being used. So if we take this same example and we look at it with pipelining, we have, yes, I'm going to start with this one. I'm going to go ahead and get my instruction. I want to fetch the instruction. But while I'm also fetching the instruction, I'm going to go ahead and update my program counter as I'm decoding this information. I'm going to go ahead and fetch it. I'm going to update my program counter. And then simultaneously, while I'm getting that, I'm also going to get memory. I'm also going to get information for the other. I'm going to start loading the other set of data. So now I can start loading this other set of data and not just have to wait for this last one to be finished. So that means I can run all of these things simultaneously instead of just looking at one particular function or one element to finish. So that is one way where we can optimize it. And this is how it looks kind of as we go through this data flow, this instruction data flow, right? All of these are being used at the same time. I'm maximizing my elements here in my computer. And while this is being, so right now what I'm doing is I'm fetching this address information while I'm executing this line, right? This is being executed. The other one is being decoded. And that's kind of how we want to look at this element overall. And I can actually, let's go ahead and update that briefly so we can kind of see where that is. So in this one, all I'm doing is fetching, right? I'm fetching this item here. All right. You can consider this one. Now I'm taking this and I am decoding this. Same instruction. Now when I get down to here, I'm going to go ahead, update the counter, and I'm going to go ahead and start writing this to my memory. I'm going to do memory and also writing to the block. So I'm going to do these both here in this kind of in the same area. And then once I'm done with that, then I can go to the point where I can actually execute it. That will be my last item where I can go in and kind of execute that. Now, when I come down here to kind of this pipelining architecture, what I can do here is the first thing that I'm doing is I'm going to go ahead and fetch instruction one. It's no pipelining. I'm going to go ahead and fetch instruction one. While I'm fetching instruction one, I'm going to go ahead and decode instruction one, or we call this what's on line 3. I'm sorry, I'm gonna fetch what's on line 2 while I'm decoding what's on this line here. Then once that's done, I can now start fetching this item here while I am decoding this, and we'll say that we're just executing this or we're doing the memory address for this particular item. So you'll see kind of how we are now moving down the line and we're going through these other items here, right? So it looks like now I'm not just doing one, not just dealing with one particular element here, but I'm doing multiple processes in the same line. All right, so that's basically how we deal with that. I have all three of these processes working together. I'm gonna try to make this here in this line. And that's pretty much what where we see the difference at. Where now, if I look at the last item for this pipelining, I'm using a lot more processes and I'm doing three actions all in this kind of same in the same clock cycle. Okay, now the next thing I'm going to do is let's talk about all of the stuff that we dealt with here. We were really talking about um we were using what's called instruction pipelining. That means for my instructions, that is what I'm using to maximize efficiency. That's what I am using to pipeline. But there are other forms of pipelining too. So instruction pipelining, it's going to separate your instructions into different stages, and then they are the things that are operated on these different in these different stages in these different pipelines. There's also something called arithmetic pipelining. And what that's going to do is, as it sounds, what that does is it splits up the mathematical operations. Like, let's say you have add or multiply or divide. You want to split that into smaller steps. For example, if you are adding multiple operands, if you don't just have two, let's say you have 15 operands and you're trying to do something, what you're going to do is split that into multiple smaller steps that can be formed kind of in series with one another in order to increase or to improve what you are doing in terms of your pipeline. You don't have to wait for all of that to get done in order for you to perform this arithmetic action, but you can do them in stages. The other thing that can be done is something called data pipelining. Now, instruction pipelining and data pipelining are a little bit different. Your instructions are specifically talking about instructions that you are giving to the central processing unit. It may be pulling something from memory, it may be retrieving data, it may be adding something, it may be some sort of arithmetic function. When we talk about data, that's how you're processing the data, and it really is looking at pipelining those interactions between the central processing unit and the memory. And the way that it does that is it takes this block of data, and what it does is it transforms it and then it aggregates it so that you have that is not spelled correctly at all. It aggregates that data so that you can use it in um you can combine it all, and it's not like you have similar to how we saw for in this architecture the if we're dealing with the instruction architecture and we're only doing fetching or we're only doing the decode and the other one's not being used and you have empty spaces. So data pipelining is similar in that if you have registers or you have memory addresses that maybe are blank, you may want to fill that with a little bit more data so that you can easily attain that and have access to it, and you don't have to wait for another data process to be complete while you're performing that operation. So that's what we're looking at when we're talking about data pipelining. Now, Some of the benefits of pipelining are obvious, right? One of them is it's going to significantly increase your processor instruction throughput, particularly when we're talking about this instruction processing. The other benefit is that you can do more instructions at a single time. So I can do three instructions and kind of operate those at one time as opposed to just being able to do one instruction per, cycle. And as I stated before, you have better utilization of the resources that are there. And what you'll see with that is you're going to have improved performance, right? Because if we go back to what I talked about previously, the three main things that you're looking at when you have your computer, right, is my power, my processing, and my memory. I want to have uh, a lot of memory available because I want to be able to use that and to get in and out of my programs and do things very quickly. I want to make sure I have enough power to run my computer for a long time. And I also want it to be operating at a very fast processing speed so that when I'm performing my operations, I don't have to wait a long time for it to finish or to execute. So you'll see that improved performance in terms of processing speed and maybe even processing power, right? If you can do these things and I can optimize how that processor is being used, then I won't just have it be idle, which means it's going to be more efficient in terms of um, the capability to handle some of these situations. Now, with every uh, where there is great power comes great responsibility. Anyway, so although pipelining absolutely has some benefits, just like everything else, it also has some disadvantages. And three of the common disadvantages or the common challenges that we have in instruction pipelining is something called data hazards, or control hazards, or structural hazards. So let's go ahead and step into these and look at each of these independently to determine what they are. When I'm talking about a data hazard, that means that an instruction or an operation needs the data from a previous instruction, right? So if we had this, right, we're familiar with this. Let's say I want to add the items in register 1 and 2, and I want to put those in register 3, right? So I have these two operands I need to access, and then I need to store them in another memory address. Then I want to take that and I want to compare that to whatever is in register 5. Simple enough, right? Well, with pipelining, what I would normally do is I would go ahead and fetch that first command, that first instruction, and then I would go ahead and fetch that second instruction and I want to start working on it. Well, the problem is that when I try to fetch this, I don't have the most up-to-date information for my R3 because the information or the operation in the previous command hasn't finished yet. If I try to do that, if I try to compare this to or get this, if I just try to retrieve it, it's not going to have the most recent information. So right there, that's kind of stopped with my ability to write that or to get it because the address is not finished. It's not the previous operation is not done. So that's what we see when we're talking about a data hazard. I want to get this register, but I can't get that information yet because it hasn't been filled by the previous operation. The other thing is something called a control hazard. Now, we talked about operations that change the control flow of a program. Typically, you want to operate your program from top to bottom. That means you're going to do this, do A, B, C, D, E, F, G, all the way down the line. But then we have these things called if statements and jumps and conditional loops and for loops and all of those things, which sometimes are called branching statements. If this happens, then I want you to jump to another label or another part of the program. If this is greater than or equal to this, what I want you to do is perform another action. But in my program, I might still have something that is directly after that that I don't want to execute yet. So when we come into these things, what might happen is that it's going to disrupt the pipeline flow because all the pipeline is doing, right? As we see this from here, the pipeline is just saying, hey, let me pull this information. Cool. Let me pull this next instruction and I'm going to start on it. Let me pull the next instruction. I'm going to start on it. But if you are jumping to another completely different section of the program, then that creates a problem because that means I don't need to fetch the subsequent instruction yet. So let's take a look at this, right? This is basically saying if R1 is less than or equal to R2, or in other words, if R2 is greater than R1, I want to jump to this target, jump to whatever is labeled target, right? Then the next instruction says add R3, R4, and R5. This would normally only happen if this is not equal, right? If this is not met, then I want to do this. But if it is, and I start fetching this instruction, then it creates a problem, right? So we get to this point, we start pulling this, then I want to start pulling this to operate on it. Immediately, hey, there's an issue because this may be fetched or executed improperly if the other loop is taken, if that other branch of the program is taken. That is what we call a control hazard. So an easy way to remember it is your data hazard is going to involve accessing the same memory address or register based on what was needed from a previous command. Control hazards are going to happen when the control flow of the program is changed, right? We talked about that in a couple of other slides where we have kind of those things that change the control flow. So if that does happen, pipelining may create these control hazards or have these control hazards. Now, the third one is called a structural hazard. Now, here's where this happens. Let's say you have keep in mind, this is all based on the von Neumann model, right? There's one memory address, one memory bus for both your instructions and your data. So if you have an instruction that needs access to the same hardware, i.e., the arithmetic logic unit or the memory bus, a particular portion of hardware, that memory address or ELU at the same time, then what will happen is you will create this hazard. So let's look at this for example. If I want to load this instruction into R2, I want to do something with this memory address. I'm going to start here. I'm going to fetch this command. I'm going to decode it. It's going to tell me what I want to do. And then I want to go ahead and then store this into this particular item. What happens here is that now I'm accessing the memory address here, and I'm going to go ahead and write to it. And at the same time, because these are in parallel, this also wants to access that same portion of memory. It may, or the same hardware. It wants to access the same memory bus. Even though it's not the same address, it wants to access the same memory bus, and that is being used by this load instruction. So what that creates is this structural hazard, right? So those are kind of things that we will see as we deal with pipelining, particularly in the von Neumann model. But there is one way, if you only have one memory address, this is where you can see that because both instructions are trying to access that memory address simultaneously. So you'll see that just like we talked here on if I'm running these at the same time, I'm trying to do this and this at the same time, this is where I will see it, right? One memory bus for both of these, one. But if I look at the Harvard architecture, I mentioned that previously in week one. The Harvard architecture is very similar to the von Neumann. The difference is that it has a different instruction both bus for both the memory and the it has a two memory buses. One is for the data and one is for the instructions. So that means I can access the memory bus for the instruction while I'm also doing something different for the data memory bus, which will reduce some of the pipelining control hazards that you would see if you're just using one memory bus for both. Right. So the Harvard architecture will kind of reduce some of those challenges there. Whereas the von Neumann, you're going to see more of those because you're using one bus for both the instructions and the data. All right. So let's go ahead and move on to the next item, the next topic. So we talked about all of these things are helping us to improve the speed and efficiency of our processing, right? If I can do this pipelining, then that means I can significantly reduce the amount of clock cycles that it takes for the entire program to run, and therefore reduce the I'm sorry, and therefore increase my processor efficiency by decreasing the amount of time it takes for the program to run. I can also improve this by adding additional hardware. Like if I think about this Harvard model and I add additional memory bus or something else for the instructions and the data, then I can reduce some of those control hazards that I might see with the instruction pipelining. And another way that we can increase or enhance our computing ability is by doing something called parallel computing. Now, two of the common types of parallel computing architecture are the single instruction multiple data or SIMD and the multiple instruction multiple data or MIMD architectures. There's also multiple instruction single data. I'm not going to cover that in this class, but that also is available. But these type of parallel architectures allow us greater access to being able to do um, multiple instructions. And as this implies, so before we were talking about instruction pipelining. Now we're looking at that last element on the list where we're doing more of data pipelining, right? I can go ahead and do enhance and increase my instructions, but I also can improve or in my data by pipelining those and doing parallel processes on those. So let's look at how that looks and let's look at some examples here. So SMID and MIMD uh, are both parallel instruction processing techniques, uh, and they help you increase your processing speed. And they are used in modern computing today, right? So they basically say instead of you doing data and just using one data point, I'm going to use more than one, right? And there's multiple ways that you can do that. So if we look at Sorry guys, I don't want this all to show up in one I don't want this all to show up in one task. What I want it to do is, and we're also gonna fix the spelling errors here. Let's add animation. We're gonna do this by paragraph. All right. Okay, so for your SIMD, you're gonna take one instruction and you go to apply the same operation across multiple data points. Good example of that is let's say I want to add something to register or add multiple items to my data. I can use this process for that, right? Let's say I have two instructions, A and B. Um, and or I have two operands. This is one instruction. I'm sorry. Oof, I'm very sorry. I have one instruction because this is a single instruction. And let's say for some instance, I want to add these items. I want to add these one to another. What I can do is set these up as data points across different points and just add them each, right? If I can add A1 and B1, A2 and B2, add these all together, and then I can access them rather than waiting for one part of the other data to be completed. So when we talk about single instruction, multiple data, that's kind of how it looks. One operation, one instruction, right? The instruction may be add A and B, right? That may be your instruction. I'm adding element A to element B, which we see here, right? This is our instruction. How do I do that? I can break these up into smaller points and add up each of these points in order to complete that operation. Before we go on to the next slide, let me just go ahead and add an animation here. Okay. Now, when I look at multiple instruction, multiple data, um, as you see back here, this has one instruction, add A and B. That's your instruction. When I look at multiple instruction, multiple data, I'm going to take multiple instructions and I'm going to go ahead and handle those things on different processors, right? This is where you get this multi-level, multi-core processors. This is where this becomes really good and really effective to use because now I can do not just a single instruction, or I can do a lot of these on a completely different processor. And this is kind of pictorially what it would look like, right? If I have this data pool, I can pull off multiple data points here, but the real thing is that all of these instructions, I am doing these instructions all independently of one another. I'm pulling from this instruction pool, and for each of these instructions, I'm operating them on different processors. I'm operating them at different points of time. It may not be simultaneously on the same processor, but it's going to be on a different processor, but I can do these all kind of in parallel. So let's go ahead and compare these two. For our SMID, it's the same instruction, right? As it indicates, it's a single instruction and it has multiple data points. For the multiple instruction, multiple data, it also has multiple data points, but rather than one instruction, it's going to have multiple instructions, right? Those are the two main differences. For your SMID, what you can do is you can do and look at those data points. Um, excuse me, let me just go ahead and update. No, okay, I'm gonna keep that there. I'm gonna keep that there because I don't know if I can do this. No. All right, I'm gonna keep that there. I'm gonna keep that there, and I'll update it later. All right, you can execute on data points simultaneously. For the MIMD, you execute on data points independently, right? Because they are on different processors. Now, for your SIMD, these are going to be really good for data parallel tasks, and they're going to allow you to do different things with let's say you have okay. Like I was saying before, you have maybe you want to add really large numbers or you want to do something that requires a lot of data operations, but it's one big command. You might want to use SMID for this. When you have something that's task oriented or task parallel, like I need to do that, and etc., then your MIMD is going to be more effective and more accommodating to multiple tasks. Now, for your SIMD, you're going to have a very high throughput when you have these high data test items. whereas the MIMD is going to be really good for flexible and diverse workloads. Now, what you will see is that maybe if you try to use MIMD for these high data tasks, you may not get as high as a data throughput because you're doing these all on different processors. So it may take time to kind of go back to the original form that you were looking at. But both of them kind of have their advantages in terms of improving and speeding up your processing abilities. So, huh, interesting. So some of the applications for the SMID are going to be graphics processing, doing something with digital signals, and also kind of scientific simulations. So if you want to do a lot of things, like I was saying before, with numbers and equations and calculations, you really want to do that. SMID will be really good for that. When you process graphics, pictures, and images, and you're like, I know what this pool is. I know what this pool of data is. I don't necessarily um need to have this on a different processor right now because maybe I want to improve the color on this, or I want to increase the contrast. Something that I want to do with graphics, I would choose more than likely this kind of single instruction multiple data approach because it's going to allow me to use the same data source. Like graphics are a really good example. Big pile of just information and pixels and all of that, lots and lots of data, but they all are connected and they relate to each other, right? So I may not want to use a different processor for that because I have this huge data pool. But what I can do is if I can handle that instruction on across multiple data points, then that's going to be effective for me doing like these contrast changes or enhancing colors or doing different things like that. Now, when we look at the me MD, this is going to be really good for your complex computer systems, multi-core processing, clearly, because you're giving each of the processes a different instruction, right? So you're maximizing or you're helping those that multi-core processing to be a little bit more effective, a little bit more efficient. And it's also going to be good for distributed computing environments. So you'll see kind of where those are going to be used in those areas. Now, all of these things are things to consider, and keep in mind, all of this is going to tell us how we can improve the processing speed of our computer overall, right? Power, processing, and memory. We talked about memory already, caching. We looked at ways to improve our memory access through caching techniques. Now we're looking at, and we also talked about improving processor overall for the hardware by adding additional processors and how effective that will be. What if you get to a point where you cannot add more processors, right? Or as for from Amdahl's law, we know that you're not going to get a one-to-one speed increase. If I put two processors into a system that formerly had one, you're not going to get 100% increase in throughput. It's only going to be based on the amount of time that you use the processor. But what you can do is through these instruction pipelining ideologies, you can still improve your processor's performance by decreasing the amount of time it takes to perform or run the whole program, right? So that is the lecture topics for today. Now these are kind of my sources. Of course, I'm always going to have this guy here because um yeah, the Carnegie Mellon University is a great source. But a lot of these I took from these sites here, which you will see in your in the slides presentations themselves. But that's what I have for today. What you guys want to do is some of the concepts here will be on the final exam, but if you listen to me babbling and you understood it, you'll be fine with the questions that are asked there, and you can always refer back to the slides. Okay. All right, thank you guys for joining me. There will likely be one more lecture this week where we will go over uh how you can use AI or a form of predictive modeling or predictions in C programming. I know you guys are looking forward to that, so we'll spend a little bit of time on that. We may not go as in depth into it as I want because we are now in the second to last week, and I know you have a ton of assignments to do. So I don't want to overwhelm you with information. Because this is an expedited course, I won't be able to go over it fully in detail, I will at least try to spend a little bit of time in the next lecture on that. All right, guys, please enjoy the rest of your day. Keep in mind that that next week is the last week of class. Friday, July 18th is the last week of class. Everything is due that day. That is due. There is no extensions after the 18th because we are supposed to have the grades in um like 2 days after that. So whatever doesn't get done won't get done after the 18th. So I would advise you now to go ahead and take the time to do with the things that you can. The final exam will be released, should be released Friday of this week, which will give you about 7 days to finish that. It will be in the same format as the midterm, where you will have um, the written portion. You will also have a slides portion, the recitation, and then you need to just, get your question. All right. So that's all that I have for you guys today. Please enjoy the rest of your day, and until next time.